Morning. Not too wet? Yeah, that's kind of how it was when I came in too. Ah, yeah. Well, they got to get you hooked. Especially in these times, there's still business there. It's still got to be pretty difficult. All right. So last time we talked about synchronous granular synthesis, where the synchronous there means you really carefully select when do grains start and what are all their parameters. And then this asynchronous granular synthesis, as I want to talk about as the first topic today, is related. I mean, the program is really similar, but all the parameters for the grains are randomized. So the kinds of stuff to know about it and the ways it's set up, and in fact, even for much what it's used for, is very different. One of the things that you've heard this before, and I mentioned it down here, if you have a non-harmonic sound, like some sound that doesn't have partials that are near multiples of the fundamental, this more randomized grains with controlled randomness is actually a common way to pitch shift, because you can't use the pitch shifting algorithm you did for homework. The pitch shifting algorithm you are doing for homework. Oh, by the way, that homework can't be due on Tuesday because Tuesday is a day of rest. So we'll just make it due on Thursday. I do want to keep up with the homeworks though, so please do keep track of what lab is assigned. I'll send out an email. Good morning. I'll send out an email, and I will write that down now. Email. And I'll have the next assignment, but the next assignment will still be, even though this homework will be next Thursday lecture, the one after that will be due again normal, like on Tuesday. It's just too hard to do the lab scheduling if we drop out 2 days of lab. So we're going to do, anyway, I will send an email about that. But the homework you're doing really wouldn't work for bells. It wouldn't work for non-harmonic sounds. And so what if you want to time stretch bells, or you want to time stretch something like that? You've heard this effect already. It's done with adding randomness and doing these grains with some controlled random parameters. But you've heard that in that overtone singing. You heard the overtone singing example I played some number of lectures ago with regard, I believe, to tuning topic. But in any case, in that example, Benedict Slotty was using a granular pitch shifter that he developed and uses in the Egan matrix. Now, I'm going to play you some more bell examples today. In this case, they'll be from Kima. But yeah, so that's sort of a time stretch thing. But the other thing that's often used is for textures. And I will play you an example here. This is a granulated sine wave. So what does that mean? Well, you got grains, and these grains look pretty much like two-phase oscillators like it did last time. You got this one here that makes the window table. It has a saturating add, just like last time. It has an index and an increment. So this looks very, very much like last time. If you use these things in Egan matrix, I got to fix these examples here. It turns out these are the column headings that you see in the matrix, not the things I'm using in this diagram. And I will try to get this consistent. We made some changes along the way, and I never fixed this. So yeah. So in any case, there's the thing that generates the window. Now the window length will be somewhat randomized. It's not totally random, but it's going to be randomized. Usually it has some center and some average value that you control, and then how far does it how far does it wander from the average value for this BW sub n, or the bandwidth parameter, or for this grain, or you might consider it the window length, its equivalent. So if you have, I'm sorry, the window increment. So you have, if you have a big increment, you have you go through the window fast, and you have wide bandwidth. Then in here, for this first example, all you got is a sine wave. So you're just granulating a sine wave, but what frequency sine wave? That's randomized. And starting phase can be, doesn't seem to do that much in this. I will talk about this in just a second though, or I can mention it now, for a stereo effect. Sometimes if you randomize the starting phase in the left and in the right ear, just fractionally sample different, right? That's one of the stereo cues. Where is this sound coming from? And so if you randomize that carefully, then you can sometimes get a really cool stereo effect. You can also get a stereo effect just by making left and right ear slightly different loudnesses. You know, the panning effects. All those things work. Yeah, and then there's, so the frequency inside the sine wave is what this is. This is just a sine wave generator multiplied by a window. Not too amazing, except that if you pick the parameters well, it works. So I'm going to play you first just this example here. This is granulated sine, and it's supposed to sound like a... And speaker's not on. Come on, it worked before. Yep. Okay, it starts very slowly, and I will stop talking, and we should be able to hear it. At first you just hear a few dribbles, and then it gets, then there's more of it. Okay, so that was a very time-compressed rainstorm, but it sounds pretty good. And in fact, I suggest, you know, you got this time at the end of class to screw around, to do research and investigate sound in the lab. And one of the things to do is find the splashing keyboard sound. It's called splash keyboard or something. But then, you know, control your fingers and try to make realistic sort of rain sounds. Because it's interesting, just by messing with these parameters, like what's the window length, and what are these frequencies, and how often do you trigger grains? Because each grain is, in this case, these are longer grains. These are not just two-period grains usually. They're much longer. So they're like each splash. But then sometimes when you control the window length, as opposed to how often they happen, you can get sort of different effects. Like sometimes it'll sound like you can get it to sound more like a drop that fell in a puddle, as opposed to a drop that fell on dry pavement. And you know, it's pretty neat. And so you can play the sound. Now, you know, it's randomized, but if you do it under finger control, and say you were doing a soundtrack for a show or something. You can control with your fingers, you know, what you want at different times, so you can really perform this storm. And even though much of it's randomized and sort of beyond your control, you're still generally controlling things. And if you think of like, you know, sort of environmental sound effects that were composed, certainly one of the really famous examples is the Birds, Alfred Hitchcock's The Birds, right, where Oscar Sala played Tritonium, and all those bird sounds are played. And, you know, and you say, oh, he's just making bird sounds. Well, actually, it's really quite cleverly composed. You know, there's real structure to what he's doing, to an extent, and to an extent it just sounds like bird sounds. So, yeah, so that's something to do in the lab. And then you can also mess with the parameters, you know, try granulating different kinds of waveforms, try changing, say, the S parameter on the sine wave, you know, whatever. Just sort of see where it takes you. So what kinds of controls do you have? There's a density control, which in the eigenmatrix we call F. What does density even mean? Well, it means what's the probability you're going to trigger a grain? Okay? Now, if you make that not too random, the F actually makes sense. It sounds like the frequency of the sound. If you're triggering grains at fairly regular intervals, you sort of get a center pitch. And you can mess with this in the lab if you like, So that's why it has the name F, which frequency, or you can call it frequency of triggering. But actually, I sort of mentioned this on the side here. If this trigger rate isn't very random, that ends up being what you hear as fundamental frequency control. As it gets more random, it gets less clear what the frequency is, and eventually it doesn't sound like a pitch at all anymore. But then similarly, if the grains are loud, we have the parameter, which is S inside the eigenmatrix, but here we call it F sub n, unfortunately. But this is, if the grains are long, that's the frequency you hear, right? That's just what's being granulated in sine wave. It's like if you have a sine wave playing through a fan, right? The fan cuts up the sound too and sort of makes the grains, but you hear the pitch of the sine wave still through the fan. And so, so what pitch you hear could be either of these. Then there's in the eigenmatrix, it's called H. And it has to do, that H name actually has sort of a weird history. H comes from harmonic truncation. So what the heck is that? It seems sort of like out from left field. It should either be bandwidth or it should be length of window. Well, if you make your window really short, so you have like less than 2 periods in your window, you get this weird truncation effect where your low harmonics drop out. Why? Well, you don't even have 2 periods of your of your sine wave. So now your pitch may or may not even be heard from the sine wave. It may be the trigger rate of the grains. But in any case, you get this effect where it seems like the lower harmonics of whatever you're hearing are dropping out or getting truncated out. And that's where that H comes from. There's amplitude. That's amplitude for each grain. If you make them very random, that's a very different effect than if you make the amplitudes fairly consistent. If you want to do this one grain generator for the left ear, one for the right ear, then you can get a spatial effect out of that too, because one ear is louder than the other. Then there's also the a delay that you can use. You use fractional sample delay, so you can hook it up to all sorts of things. Yeah, so it's kind of cool. I wanted to mention this little diagram in the top. What the heck is this? Well, if you have a big BWN, okay, so that's this here. This is how fast are you stepping through the window table that makes, this raised cosine that makes your window function. See, if you step through it fast, if this thing here, this envelope end parameter, BWN, is big, it doesn't last very long. So you see in time here, this blob here corresponds to one that doesn't last very long. But because it doesn't last very long, if you had a really long grain, you'd be hearing that sine wave. It would be very narrow band. But the shorter you make the grain, the less it is like a pure sine wave. So you get a big, in the frequency direction, you have a big splatter of frequencies. On the other hand, if you have a small BWN, if you have a very slow or a very small envelope increment, or if you think of bandwidth as small bandwidth, then you have the sinusoid that's placed for some amount of time, and so you get this, long-lasting but very narrow in frequency direction. Does it make sense? So you can kind of think of this in frequency domain, time domain, whatever you like. All right, so I want to play you some more examples here. Here's this you had heard already from the eigenmatrix, a time-stretched bell. Now that actually takes some work. Benedict Slotty is a brilliant guy, lives in Northern Europe. There's 2 days a year, right? There's light all day or dark all day. Light 6 months and dark 6 months. And he's a brilliant dude. So he has time to work on this and is very, very knowledgeable. And he did this in the eigenmatrix. It's a challenge to do there, but he did a great job at it. You heard that in the when I was talking about tunings in that lecture. You heard it as background to the overtone singing. Well, here's another example. This particular one's done in Kima. So here's a dry bell sound. Okay, so that's a bell you can hear, of course, at the beginning, right? It has a very different timbre than later. So here's a granulation. And what you're doing here, instead of having a sine wave in here, there's a short recording in here, right? Or in the continuum, you can also do this live, where it's just whatever's coming into the microphone, the last few samples there. As I say, to get those offsets and indexes right is a challenge. But anyway, there's a recording in here. And then you can go forward and backwards to that recording and pick random grains out of it. And so you can hear here, it's a randomized grain thing, and it sounds certainly bell-like. But you can hear sometimes when the center part of the randomized locations in the sound that it's using to granulate, when it moves closer to the beginning, you can hear the timbre change than when it moves later. So just also louder. The grains are really far apart, but you can kind of hear, just different messing around with that sample, granulating it. And so is that a very realistic bell? Well, not really, but, or at least not as realistic as what Benedict Slotty was going for in that other piece. But it depends what your effect is, right? If you want this sort of bell texture in the background, this can be extremely useful. This is actually this is a Harp Glissando. This is Carla Spoletti, who's president of Symbolic Sound. She's playing a glissando on, I think, an Irish harp, a really small harp. And so this is what the original sounds like. So this is actually pitched, or at least a sequence of fast-pitched things. But again, for effects, this isn't a rain effect, certainly, but it's a cool effect. And when I play the granulated version of this, I think it's quite beautiful, but it's hard to tell what the harp is, except that I'm going to play the harp for you first, and then you'll hear it. So here's the original. So that's the source material, and here it is granulated, again, moving through the sample much slower with different carefully randomized grain parameters. So, you could hear the pitch going up because it was granulating in fairly small areas with pretty big variation grain parameters, but not the center position. The center position was just, I don't know, it's a cool effect. And it has its very organic sort of feel to it, despite the fact that, it doesn't sound like harp anymore, but it's, so if you want to massage and make sound effects out of source material, it's extremely useful. All right. So, questions about that? So in the Egan matrix, if you want to mess with this, well, you can find that splash sound and the keyboard controlled splash, and it's just a thing to play with, and you can mess with that some. But if you look at that, you'll see there's a sine spray in there and a harmonic manipulator. So a harmonic manipulator is exactly the same thing we used last time to make all the timbres we heard last time, like that violin timbre and all these other things. But here there's lots of randomness added. So it's really just different control of identical thing. All right. We good? Okay, so the next thing I want to talk about here is this IRCAM Chant synthesis. So this is the Parisian Research Center. Of course, they've done lots of different synthesis things, but this is one that is, I think, pedagogically interesting and musically also useful. It's a somewhat limited algorithm, but it's withstood the test of time in the sense that people still talk about it and occasionally you hear it used. So I'll first play you this example and then we'll look at it more. So what we've got here is there's a tremolo violin sound playing. And that's just, actually, that's additive synthesis. And so that's not the topic right now, but we talked about that in the past. But there's a tremolo violin sound where sustains are done in additive, its own topic. But then you also hear the voice. And this voice that's sort of singing over this is using this chant synthesis. So chant, as horrible as my French is, just means singing synthesis. And it's a sort of a singing voice synthesis where you are really making the impulse responses of each resonance in your voice. So it's kind of cool because it's, in that way, really a simple idea, sort of. I mean, you have to implement it, but a simple idea. So here's the example. Listen to it too. There's something very voice-like about it. At some points, it sounds like the singer may have a bit of a sore throat. If you really want a singer, I'd go get a singer. But I think it's quite a beautiful, interesting sound. Now, this is a synthesis algorithm we don't have inside the eigenmatrix. So that example was from symbolic sound schema, and I just wanted to show something that uses it. So yeah, so you can do different vowel sounds and such, and it's a bit otherworldly, but pretty in its own way. So this is what the Chant oscillator looks like, and the idea of it is that you have a window table, but it's not really window shaped now. It's this sort of generic glottal pulse shape. This is a glottal pulse exponential decay shape. Okay? So that's what this really is. This is a decay, and then you have a sine wave here. So you can make a decaying sine wave. And just a decaying sine wave isn't so interesting, of course, if you just have one. But what if you trigger it every glottal pulse? Then the decay rate here is controlled by this BWN parameter, and the frequency by this F sub n parameter. So you get this decaying sine wave that's triggered every glottal pulse. Okay, and the decay rate has to do with the resonance frequency. So what this really is doing a single resonance of your mouth. Right, and what the resonance frequency is, how fast the resonance dies out. I'm sorry, how fast the resonance dies out. What the resonance bandwidth is depends on your slope here. How big is this number? If you want a resonance that is a very narrow band, well, a narrow band resonance dies out very slowly. Now, there's not too many of those in voice, but, you can make more narrow-band ones than others. If you make this narrow band here, or make this last a long time, bandwidth being a small number, this will last a long time, and this thing will die out very slowly. And by the next glottal pulse, it'll still be going. So you need another Chant oscillator, another one of these grain generators of this sort, to start at the next one, and maybe even overlaps with the third one. So you might need 3 of them just to make this one resonance, because the resonance decays wrong. But that's actually unusual. Usually the resonances die out fast, so the oscillator will be available again. It'll be at the end of its cycle, and it'll be available again next glottal pulse. Does that make sense? So that's the resonant bandwidth. The resonance frequency is just, well, what sine wave do you have under there? So it's actually, not so different from this, right, except it's a different shape here, and you're granulating a sine wave. But here, the way you're thinking about it is this is an exponential decay on a sine wave implemented this way. So what the frequency of your resonance is, like where is your formant or where is your resonant peak, that's determined by the sine wave. So it's kind of cool because you have independent control now over what frequency are your resonances and what frequency is your fundamental, right? Because the fundamental frequency is just how often you trigger these things. That's what you're hearing as a fundamental frequency, as a trigger rate. But then what the frequency of the resonance, that depends on whatever you're doing here. Does that make sense? So that's kind of cool. Now, for most voice, you want at least 2, probably 3, maybe even more resonances. So at each glottal pulse, you want to start, say you have 3 resonances you want to do, 3 formant speech. You want to start 3 of these. 1 for each, and the 3, depending on the bandwidth of the resonance, of the particular resonance, of each of the 3 resonances, you have 3 different decay rates, 1 for each. And then depending on the frequency that that resonance is centered at, you have 3 different frequencies. So basically you need 3 of these whole things, 1 for each resonance, and they start every glottal pulse. So you can think of this as like just making an impulse response for 1 resonant filter. And well, you need 3 impulse responses because you want 3 filters, you want 3 resonances. So yeah, you have 3 of them. We good? So yeah. So there is a question here. How many Chant oscillators are needed to make a single sound? It depends. If they overlap a lot, you need more. And if you want more than 3 resonances, you need more. But I'd say on the order, if you have, for most things, if you have 32 or so of them, that's going to be enough to make most of the stuff you want to make. If you're doing this in software and, you aren't worried about running out of computation time, it doesn't really matter. You just make as many as you need. We good? Now, in the eigenmatrix, we don't have this algorithm, but we have an algorithm that was actually around much earlier by Georges Genie, a Frenchman, and I want to show you that. So this much predates that algorithm and much predates a lot of things. It's, again, just one of these things where somebody brilliant did something long ago. The best implementation they could do at the time was still good, but now you can do even better. And there's a little comment I made at the bottom, which is, I guess, off the page here. But this is very useful, especially in conjunction with other eigenmatrix modules. So as far as I know, the only modern implementation of this that exists is in the eigenmatrix. There are, of course, still ondiolines, the instrument, the original instrument around, but other than antique instruments, which still work, there's the eigenmatrix has the only implementation of this. And one of the things that, again, makes it so powerful is that you can hook it up to other stuff in the eigenmatrix. Early in the history, we talked about Bob Moog, right? And his, there were already analog voltage control synthesizers before him. People are already, before him. People have done all this stuff already. But to make it voltage control and make it so that you can connect things up and not, just do knob twisting, but so that other parts of your circuit can control your circuits is super. And that's what really made the modular synthesizer, and that's why it's so special. Well, here, these synthesis algorithms are cool, and they get you, 80% of the way there, or 90% of the way there, or maybe even 95% of the way there. But it's really useful to be able to hook them up to a few other things just to mess with it a bit. The example I'm going to play you here is, let's see, I'm going to play you 2 examples, and then we'll talk about them more. The first thing is the Genie sax, and yeah, well, I'll maybe I have more things I was going to say about it right now. I don't. Yeah, it looks like Jenny, but it's French, so it's pronounced Genie, like genius, and I assume he was. It sure looks like it. My comment here was that Genie's method is really great for reed sounds. It's very controllable, and it is very difficult to get attacks right. In fact, this isn't the go-to sax sound that usually the physical modeling stuff, which we'll start today but get into more tomorrow, next Thursday. The physical modeling stuff is what most people use. It's just too hard to get the air sounds, get the attack right and stuff, but still, it's quite pretty here. And even there, it's hooked up to other modules. That's not the. If you listen to Ondiolin examples online, you're not going to hear these sounds, and it's just a matter. Yeah, well, he was before there were modular synthesizers. He didn't. It wasn't possible to combine it with everything else. Here's another example. This is a Genie trumpet. I just got this recording, so the one that I had distributed earlier, I don't like as much as this. And this just has some tiny little improvements. So like one of the things is, so this is a trumpet sound, and again, it's also hooked up to other modules. There's some resonance controls that are done with biquad bank and that sort of thing. But the core of it is the Genie Oscillator trumpet. If those of you listening remotely want to hear this, email me, and I will send you a version of it if you want a better copy than what you can get here through Echo 360. But in this example, there's just little improvements. This is a jazz example that Ed Egan is working on as we speak, and he just sent me this excerpt, yesterday or something. So it's a documentary about Stan Persky. But in any case, in this example, the trumpet is done with a Genie Oscillator, the core of it, and one of the little things that makes it just a little bit more believable, nice, is during the attack, you put in a pitch blip. And if you remember from homework 1, if you look at the frequency graphs and the amplitude graphs, there were these weird excursions right in the attack, and hey, that actually really helps. The other thing is that he also did this other trick where there's some glissandoing going on here. So there's some sliding between notes, and well, the trumpet valves are really their own thing. When you're sliding smoothly between notes, it's sort of this quantized instrument where you're not using it in a quantized way. And so what he did here is, you can hear the smooth pitch slide, but then he tried to quantize just slightly, tried to quantize some of the timbral changes that happen as you change valves. Anyway, just something to listen to. There's a bunch of other instruments in here that are also interesting synthesized in the Egan matrix, but I will play you this example here. It's all synthesized, yeah. Yeah, so the violin sounds you heard in there were done by the same as the 3 pieces of string I played last time. It's synchronous granular. It was a little hard to hear in this example. There's a little bit of sax in there. That's somebody we'll talk about next time, not the sax I played earlier this class. And the trumpet is by this Genie Oscillator in the core. The piano is, fundamentally on the continuum. Piano, if you want a piano-like sound, it just isn't the right instrument for it because piano is struck by a hammer. So the piano is done with Modart's physically modeled piano. And one of the things that makes this sound so good, there's so many cheats here, like for the percussion tracks. For one thing, sampling can work pretty well for percussion, but what people miss in sampling all the time is that, hey, a lot of what makes music alive and organic isn't the individual notes. It's overall how it's played. And in the percussion tracks here, Ed told me, well, he has some software which I would advertise, except I don't know the name of it, but where they recorded and extracted timing for very good jazz percussionists. And so you start with that, but they made MIDI data out of it, so then you can, if you don't want a certain symbol or you want a different sound, then, you can substitute different things for it, but at least the dynamics are there. And there's, the brush effects and stuff are iffy, but again, if you're really careful with it, even that you can make up for. So it's pretty good. And, for me, it's always been sort of sad because I make this instrument in my basement that's just too expensive. I don't even have to make a living at it, right? I got a day job. But still, it's so expensive to make that, jazz artists just can't afford it, right? Most people are struggling on a good day, now where all the gigs are shut down, man. And so it's been very hard to get into the jazz community just because it's just too expensive. And also, it's not for everybody, right? Unlike a keyboard, you don't know if you're going to like it. You have to spend some time with it before you figure it out. And so, So I really like this example for lots of reasons. But yeah, it's all synthesized, although it's very carefully done by Edmund Egan, who I can say is one of the world's best sound designers. And is fortunately not in Hollywood, so he has time to work with me. All right. So I really like that example. I got some other examples here, like melodica. Right, that's a keyboard, a cross between a keyboard and a harmonica, I guess, or whatever. That kind of instrument. It's interesting unless you know details of the melodica sound. I think it's too hard to hear. So, questions about that? All right. What is next here? Okay, oh yes, so I was going to say, well, how does this work? I used to always play the examples last, but I think it's easier to stay awake if you actually hear what it does. Hey, I was just talking about you. Anyway, I played your documentary excerpt, but I got to get back to talking. I'm in front of people here. I'll call you back in an hour.
Okay.
Hey, is that switch going to work?
Yeah. Okay. I'll talk to you later.
Okay, bye. Anyway, by the way, thank you for not answering the phone. It is awkward for me when I work with world-class people. I can't just always blow it off. So I apologize for that. Okay, so master oscillator, Genie, yes. Oh, Genie Oscillator. I still say Genie. I can't help it. I should know better. Genie Oscillator. So this name Genie Oscillator is just a name we came up with. I mean, I want to. Uh-oh. I'm kicking the ground connection here. This Genie Oscillator is just a name I came up with to describe what we have in the Egan matrix. And this is in the Egan matrix. Again, if you want to mess with this, find one of the sounds, though. and start with that. In the building block section, there might even be some building block sounds. The problem with those is they show you just one item, and a lot of these synthesis things are, the individual technique is kind of dry. And you can do some cool things with it, but it always sounds like a lab experiment. Where if you pick a sound that already does something, it's harder to figure out, but at least you start with something cool, and then you can mess with it. So it's up to you. But I would say, when you, in the building block section, if you're spending your time in there, the problem is you're not learning anything from these world-class sound designers. You're just sort of trying to use the stuff yourself, and it's as if you just learned how the chess pieces move, and now you're going to play chess. That's great, but it's still worth it to also, look at great chess players and what were their opening moves. What kinds of things did they do, and learn about that. Because just knowing how the pieces move is very far away from being a grandmaster. Okay, so the master oscillator. The master oscillator here. This is just a normal oscillator in the eigenmatrix. Okay, so in this implementation. Now, what does a normal oscillator have? Well, inside it, I didn't draw the whole phase oscillator here, but inside it, it has a phase accumulator. So pretend there's a, that feedback thing there. And you get this band unlimited sawtooth. You get this phase, I shouldn't even call it sawtooth. You get this phase that increments and then goes back, drops down, increments, drops down. So that's the master's phase value over time. Okay? And that indexes in the sine table, so you hear that oscillator. So you have a sine wave oscillator, that's the master. Cool. Then to the right of it in the eigenmatrix, you make a Genie Oscillator. And the Genie Oscillator is sort of like the master oscillator, but it only has half a brain. It actually borrows information from the master. And it seems like, well, what's the point here? But anyway, Georges Genie was extremely smart. So this was back in the 1940s in France. So bear with me here. The first thing that happens here for this other sine wave oscillator, which is a Genie oscillator, because it's special, what Genie oscillator really means in eigenmatrix, it's using the phase of the master oscillator in nefarious ways. Really useful, weird ways. But it's really locked in with the master oscillator. Okay? So what's going on here? So one of the things it does, it takes this phase value and multiplies it. Multiplies it up. This multiply factor is usually 5 or more. Doesn't have to be, though. The exceptions always work too. But what is this here? This is basically choosing what is the resonant frequency you want. This thing really here, you're going to make this just like you did, just like a Chant oscillator did, which is a much later invention, but a similar idea. Just like in a Chant oscillator, you're going to make a decaying sine wave out of this Genie oscillator. And you need to pick a center frequency for that decaying sine wave. It doesn't have to be an integer multiple of the fundamental, but it's some multiple of the fundamental. Usually, 3.7 or 5.8 or whatever it is, and it depends. If you want a resonance, say, at 710 hertz, and your fundamental frequency is 330 hertz, well, this multiplier is just 710 divided by 330. Right? Because, so you have to be clever about how you choose this multiplier if you want a resonance that doesn't move around all the time. Yeah, so you, but the math is easy enough to do in the eigenmatrix. So this is a frequency multiplier, and it says what the resonant frequency is going to be. Now, if you want several resonances, you have another Genie oscillator. And 2 is usually enough. There's such a thing as trying to add more and more and more, and more doesn't always make it better. So 2 seems to be enough to get interesting effects, and spending your time just on practical advice. Me not being a great sound designer, this is what I pick up from others. Practical advice is don't go beyond 2 if you're doing this. In fact, just do 1 first and see if it works at all. Try to figure it out first. But so there's another resonance here. Okay, so these are multiplies of this fundamental. But what is really happening here? This master phase goes 0 to 1, is sort of which is 0 to 360, right? Now you multiply by 5 something, so it goes 0 to 5.5. point thing. So what happens because of the way the overflow math that I used is implemented here, when you multiply this, it just wraps around. You know, it just goes through 5.1 cycles for every one of these fundamental cycles. Now, you don't want anything to go through just 5.1 or some fractional number of cycles for each fundamental, because by the time the next fundamental period starts, you're going to be 5.1 way through some period, and that's not good. But there's another trick here. He makes, Genie uses the same phase thing here. Now here it's multiplied up, but here it isn't. Here it's just reversed. So if you look at number 2 here, it's a reversed, it's just this thing here reversed, and that's just a linear decay. So what's going on here? So you have this thing that does 5.1 periods, but it has a linear decay on it. It's going to die out in the fundamental period. So so it's going to get down to 0 when it's 0.1 of the way, because its amplitude is going to be 0 by the time it's 0.1, and that 5.1 times frequency. By the time it's 0.1 through that thing, it's okay. There's not going to be discontinuity there or anything, because it's going to be smushed down to 0 by then. So this is a linear decay. Now, in the Chant oscillator, you had a nice shape of a glottal pulse. Okay, this isn't quite that. There's less choices here. This is 1940s. Now, in the Egan matrix, I did add some more choices, so you can do different kinds of decays. Like I drew some of them here. You can mess with those parameters. They do sound different, but fundamentally, it's still the Genie oscillator. And you can do these different things, and they do matter in the sound. But I'm not at all, because I added extra bells and whistles, but I'm not taking the thunder from George Genie. He came up with this. And this is a re-implementation with much newer hardware. Anyway, so that's multiplied here. So all this is this sine wave has a decaying amplitude here, and this is another one, different, decaying amplitude. Now, how fast does an amplitude decay? Again, in the Egan matrix, I let you set that. You can multiply up the decay factor. You can make it faster than 1 period. But with this setup that you see right here, you can't actually make it longer than 1 period. So what it means is you get pretty wide band resonances here, because it's got to decay out before the next period. But you can, as you heard, you can do a lot with that. Also, I have a research student this semester who is working on making for more narrow band resonances. We'll see how that works. He's doing a senior thesis on it. I had some ideas for that, and never had time to implement it. But I think he's going to be successful. So there's other things you can do to make the resonances last more than 1 period. In any case, yeah, cool thing. So these notes over here are just things I already mentioned. In the Genie trumpet, one of the tricks is to do a frequency blip at the beginning of the note, and also for glissandi to try to do. So this Genie oscillator, along with its master oscillator, then goes into another thing that has resonances, into a big bank, I believe, that has resonances. I mean, he just did this yesterday, so I think this is still true. But those resonances, they're pitch dependent, but they're quantized. So it turns out that you get just a little bit of this valve effect. Cool. Are we good? All right. So I'm going to do a major new topic now. Unless I have some last minute questions, I'm going to drink some coffee. Also, I'm getting old enough, I'm kind of stiff. So if you got a question that you think of, let me know. Otherwise, we'll go on to the next thing. All right. So the next thing I want to talk about is physical modeling. Now, actually, in some sense, algorithms we've already talked about model instruments. For instance, the subtractive synthesis thing, we had a very simple subtractive chain that Mark Smart came up with, who's does work in the building. He's an interesting guy to talk to. But and he implemented that first in the analog world, but then also as a reactor implementation of it. And students have sometimes done that for projects here too. So, he had that sax sound that I played for you quite a while ago, and when we first started doing fixed waveforms, and that's a physical model in a sense, right? Because you're modeling mouthpiece, you're modeling the bell, with simple filters, but sometimes in physical modeling, I think you have to be a bit careful. It's really easy to convince yourself that you're actually doing this amazing, different thing. It is true when you're physical modeling, there are important ideas there, but keep in mind that the level that we simulate the world at is pretty basic. And that turbulence and stuff, even the best supercomputers have a heck of a time doing that, and nobody really knows how to accurately simulate the turbulence in musical instruments and the real nonlinear feedback systems there, even with supercomputers. So keep in mind that the physical models, it has the same attraction as a lot of AI algorithms do. If it's not understood very well why it's doing what it's doing, then it's magical and everybody thinks it's great. And physical models are, there's less magic there than you would think. So I want to say that as an introduction because I always have this worry that people think, oh, the synthesizer is doing this on its own. The sound designer is really good, but a lot of the reasons the continuum and the eigenmatrix sound so organic and it's getting all this worldwide attention is because of a great performance. Like that performance you just heard is done by somebody who has very good ear and is very careful and has really practiced playing those individual sounds. They're not, they don't play the violin sound the same way they play the trumpet sound. It's not just pressing a button on a keyboard and playing it. They're really interacting with the sound. And their skill at playing is a lot of what makes this effect, just as it is in the acoustic world. If you're blowing into a trumpet in the acoustic world and you don't watch what you're doing the whole time during a note, well, you're going to be out of luck. So keep that in mind. So the physical modeling topic, I think, is very important. And I'm into it. I'm into the ideas. But keep in mind that you can also get fooled by it, especially when I get too excited about these great things here. So what is the idea of physical modeling? You're trying to simulate the physics of an instrument. That's very different than when you sample something. That's just fundamentally very different. You're simulating something. And why would you want to simulate the thing? Well, because notes in a sequence affect each other. Simultaneous notes affect each other, right? That's true in any acoustic instrument, but it's not true if you just have straightforward samples. And, in sampling, you can try to do, sympathetic vibrations. I'll just play this other note quieter or something. But it's much more complicated in acoustic instruments. In fact, in acoustic instruments, you'll never have the exact same waveform twice, ever. And no matter how much you sample things, you're going to get the same waveform out again if you play the same note the same way. So, so in the sequence of notes, they affect each other. So there's this long-term interest in detail complexity of acoustic instruments. So on the one hand, like the things that we synthesize, like this trumpet sound that you just heard played so very well, at least in my opinion. I'm still blown away by it. But that was, if you play an individual note in that, it won't hold a candle up to a good sample. No way. But what happens is if you play whole melodies with it, then, trying to emulate different parts of the trumpet, even, we don't even consider the Genie Oscillator really physical modeling, or at least it's a pretty shallow kind of physical modeling, but that actually, that's what really brings it alive. And it's not that each individual note is so great. It's something sort of longer term about how the instrument sounds, how every note is different, and how notes interact with each other. Another cool thing about physical modeling is hey, if you can model something in the physical world, what about modeling something that doesn't even exist? That's not a real thing. So I want to play you an example for that. Here is an instrument. This is a wind instrument model. Oh wait, There's even a picture that goes with this. This is a wind instrument model, and it's a sort of straightforward wind instrument. This performer, Peter Pringle, is a Canadian multi-instrumentalist. He's very famous for playing theremin, but also many other instruments. He builds instruments. He's also famous for some pop music that got him enough to live off of, as far as I can tell. He's famous for lots of different things. If you are in the Star Trek nerd community, he's the world's foremost Vulcan harp player, which was, of course, just a fakey instrument on the show, but he made one and really plays it. So if you want to go to your Star Trek convention and you need good music, hey, there you go. Anyway, so here he is playing with the left hand. He's playing a synthesized piano. With the right hand, he's playing a wind sound in the eigenmatrix. And so I want to mention a few things about this. So he's playing a lead line with the right hand, and if nothing else, it's just easier. Right? You don't try to play all of the notes. Plus, it sounds beautiful. The juxtaposition of the two sounds great. But the weird thing about this wind sound, which was designed by Edmund Egan actually, but this wind sound has even harmonics that go sharp while odd harmonics go flat. And it sounds sort of familiar. The closest thing I can think of is those plastic pipes you can swing around your head and you get, but not really. It's just that's the closest thing. So it doesn't sound that unusual, but it's something that you couldn't build in the real world. Even though it's a model of the real world, it's a hacked model. So here we go. That's in the downloads, and you can also find it on YouTube. I think it's quite beautiful, but it's not, it's a clearly synthetic instrument you couldn't actually build. So, it's simple, but very, very beautiful. And I think appropriate. Now, I'm not a piano player. Piano players, of course, don't like music change. They don't even like Mussorgsky's Pictures of an Exhibition. But in any case, I think it's great. Beautiful version of that piece. Okay, so questions about that? Yeah, so it's kind of cool to, simulate things that don't even exist. And you've seen other examples of that before. There are real questions about physical modeling, lots of different things, like, to what detail do you model? Are the details useful? What a very low level is, like, do you model each molecule? And if you don't, how do you model your turbulence? If you just do a statistical model of turbulence, it's pretty different than the real thing, right? So there's all that. And if you do model each molecule, then, well, it's really hard to get any model that works at all, and that kind of, and it's a lot of computation power. But even a higher example, you have things like violin. Okay, so one of the things that we've already talked about last time, and in this jazz example, he's using this two-handed violin thing because it just makes it easier to play things that you would expect from a violin. So even if you don't want a real violin, I mean, if you want some of the aspects that make a violin sound so beautiful, splitting between the right and left hand is actually a useful thing to do. It can also be limiting in other situations. But there's many other things. Like if you have a violin, being a not very good violinist, I have a lot of experience in these areas. You have a bow velocity versus bow pressure. And if you want to get a good tone out of it, if your bow velocity is low, you have to use much lower pressure. If your bow velocity is high, you have to use higher pressure, and you have to adjust this all the time as you're going. So that's fundamentally an important part of violin playing, but do you really want to simulate that? Do you want to make people go through gyrations so that most of whatever you could do by pressing on the surface, say in the continuum, doesn't make a sound at all but makes a horrible gack noise? I don't know. It depends, you know, because in some ways this is, you can say, oh, well, that's just a limitation of the violin. It's not very good. I'll do a better job. On the other hand, well, you know, the limitations of an instrument are always much of its beauty, too. And it's one of the reasons I can say, whatever your answer to this is here, you know, whether you want surface noise or not, the fact is that if you want a violin, you know, you got to play a real violin. If you really want it, that interaction with the instrument, you know, as soon as you abstract away how does a person interact with it, you're not getting the real instrument anyway. But I think from a synthesis point of view, getting aspects of that sound, you know, things that are reminiscent of what makes a violin interesting, I think is something to think about. So the physical modeling, of course, is a big topic. And in fact, even the subtopic of physical modeling is noise. It is easily a semester's course. I don't know if I know enough about it to do a semester's course, but boy, I hear a lot of bad noise in music. So here's some very fundamental observations that just from somebody who's been in the business or in doing synthesis for a long time, I strongly suggest you do this if you're at all interested in noise. You know, in the eigenmatrix, critically listen to the white noise. And then compare it to something you write in C or Python or whatever you want, you know, a random number generator, and listen to that. Now, both of them are flat. Both of them are statistically, you know, fine. They can be, quote, good white noise in that they never repeat the same value with, you know, if you have a 31-bit white noise number, in 2 to the 31 times, they'll never repeat the same value. All that stuff can be true of both. I'm not, you know, that's not what makes it sound good. What's weird is that the eigenmatrix noise, by the way, I did not think of this, was this Dattaro, whose papers we're still going to look at some more of later, but Dattaro observed this. The eigenmatrix white noise sounds really good. And the white noise from C has like this whistling nasty thing in it. And, you know, the randomness statistics are the same in both. But there are different algorithms for making them, and, you know, what your ear picks up, you know, you can easily say, well, your ear is imagining this. This is fabricated by your, I guess. But the whole idea of what we call randomness in our math is also a fabricated concept. You know, I mean, who's to say what's, you know, we describe the world with our math and our description isn't very good. So then we say the world is fabricating things. I don't know, you know, you can argue that all you want. But anyway, so Dattaro's, you have it in your course packet, actually, if you want to look. You know, in the oscillator, sinusoidal, and pseudo noises in there. We're not going to read that paper. I'm just talking a little bit about here. Keep in mind, he has a big table in there of things that are supposed to be equivalent. And I suspect he did that because he thought he had found everything about it and he was just going to generalize, hey, here's a table of, depending on how many bits you want, this is what you do. Well, I found that there's real differences. Now, it takes you a while to get into the groove and really know what you're listening for, but I picked a very nice function out of that table. They're not all equivalent. You know, there's yet more to it than anybody knows. But anyway, that's a great starting point, is that paper. It's the only place I've seen this discussed well. But that's white noise. And there's lots and lots of noise in the world that isn't white. You know, even if you do something as simple as shh or s or whatever, you know, or there's noise in all those things, or creaking door, all those things have noise in them, and just filtering white noise, which is a standard synthesizer approach, even if your white noise is great, doesn't get you very good results. It's very hard to make anything that, especially upon longer listening, sounds very good. So physical modeling is one of the solutions. And in the E matrix, again, if you are, oh man, I'm not getting graded for my final project, I just have to go to the lab, what a bummer. Well, hey, mess with some of this stuff. So one of the things to do with is to look at the Kinetic Model bank. There's some examples of it. Again, the building blocks are a little bit iffy here, but hey, it doesn't matter if you want to start there or start in a sound that really uses it. But what is the idea here? Well, the idea is, here's an example of one. This is a crackling noise one. Go find it. Listen to some crackling noise. It doesn't sound like white noise. It sounds like crackling. It's somewhat random, but it's not just flat. It's not the simple randomness. There's more to it than there. And so here is a thing. I'm just going to read this. The output of the one-dimensional model. So this is a kinetic model, but it's a position of a weight on a spring. And you can look in the user guide to try to get more out of this. But again, the position of a weight on a spring. So you've got a spring holding a weight, and its position is the output of this model. So you can, springs can oscillate, right? And if there's friction, then they slow down their oscillation. And if you're putting energy into it, then you can get, like say you put pulses of energy into it, then it oscillates and dies out. If you put random noise into it, it oscillates and dies. So that's all good. You can see how you can filter sounds and get interesting effects with that. But there's more to it than that. The spring is in a one-dimensional container of viscous fluid. Well, that just means how it slows down. You have control over viscosity. It's just a way to think of this thing. There's a little picture here of a spring. It's suspended from some point. You can also drag it around. You can suspend it from different points. It can, if it boings too far, it bounces off the bottom or off the top. And that can be when it bounces off the bottom or the top, that can be a hard bounce, so it doesn't lose energy. But normally it loses energy. There's some padding down there. You have control over what that is, how thick it is. Then you also have bowing. And bowing is weird because in bowing you have yet more friction things, because in bowing, as you might know, the rosin, the rosin that you put on the bow to make it sticky on the horsehair, when you pull on something, it pulls along. It just drags it along because it sticks to it. But then eventually, the thing that's sticking to it starts slipping because it can't hold it anymore. There's too much. In this case, the spring is pulling it back, so then it has some dynamic friction. But then, when there's enough dynamic friction built up, the rosin melts, and then it has yet another friction coefficient. So you have the slip-stick effect, which you hear many places. Creaking doors, is a typical example. There's lots of places you hear it. So anyway, so you also have that, and you have all this stuff. You have all these parameters you can mess with. You can control them under your fingers. Some of them, usually a clever combination of formulas that take your finger information and for whatever your kind of noise you're trying to get, take your, combine your finger information and then process. So this is really just a fancy way of processing white noise still, because the energy coming into this is usually some sort of filtered white noise. But there's lots of different effects you can get out of this. Now, a model like this, like any time domain model, is quite unstable. You'll read lots of papers about time domain modeling, and people talk about how it's stable and free. Actually, it's quite unstable, and at least the modern DSP is not a very efficient algorithm. On the other hand, it's super useful. This time domain modeling and other ones. Okay? So why is a physics model like this not very stable? Well, you have some step time. You have quantized time. And you have control over what that time is. But boy, if you change that, it really matters. You also have just number of significant digits. With floating point math in the Egan matrix. But tiny little details can really add up. I mean, these nonlinear systems are nasty in that way. And so, on the other hand, much of the interest comes from all this. So it's not, it's not all bad that it's so unpredictable, but it does make it a bit like herding cats to make sounds that, that stay stable in the range that you want. All right. So about another time domain modeling, which is often called physical modeling. It's sort of taken over that name. You know, it's much like PC means a Windows product, right? Come on, it's personal computer, you know. Lots of things personal computer. This phone is a personal computer too. I mean, the name is sort of generic, or Windows. Windowing systems were invented, you know, long ago at Xerox Labs and then used by Apple, and then, well, anyway, eventually some operating system that used it took that name. It's all fine, but it's very general words that are used in a specific way. Well, waveguide physical models or time domain delay physical models are sort of have taken over just because so many papers have been published about it and so much work has gone into it. And it is a very useful physical modeling technique, although on the continuum for real-time control and manipulation, I would say it's not the absolute best necessarily, but there are many things that you can do with waveguide modeling that I see no other way to do them. So there's some incredible successes there. And as I say, especially in academia, insane amount of time put in. Now, a lot of these modeling things are curious because people want physical models, they talk about them all the time, and then they play a keyboard. Well, if you're just going to trigger something and not interact with it, the importance of having a model is way down the list. In fact, you could have gotten a much higher quality sample of an actual instrument, because modeling something is very hard. How do you know all the physical parameters? You know, in here, we're going to model this thing, and very soon, if you keep your wits about you, you'll realize, oh, we're modeling an ideal string. And anything that makes it not ideal is sort of this add-on thing that we sort of try to jam in somehow. And it works. There's a lot of cool things you can do with that. But is it really that great a model? I'm going to interrupt you for a second. I'll be right back with a picture. But here is an example. This is an old example, and you have this for download if you're out there in virtual land. This is Pluck Video. A long time ago. So that was a long time ago. That's actually even older model continuum than what you have in the lab. And it's quite beautiful, I think. It's a very simple physical model. And, you know, when you talk about physical modeling to audiences, they ask, oh, well, you know, what kind of string were you modeling, and what, was it cold pressed steel, or was gut, or what was it, blah, 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 It's like, these are bursts of noise going into this simple delay line. So it's a modeling, and it's a cool modeling. But keep in mind how oversimplified this is over the real world. And, this blind faith in, oh, well, you're modeling the real physics, so it's this magical, amazing thing. You're approximating the real physics. And it's like deep learning systems of today. We talk big about them, and they are impressive. But they don't they don't learn like humans learn. They don't, they're very, it's very important not to get confused about what we're dealing with. Dealing with something very powerful that in some instances can even do better than a human. But in general, don't confuse that with, oh, learning is this generic concept, one-dimensional thing, and deep learning is, well, it's like people, except it's faster and uses electricity. No, it's not like that. So, and so it's not that, deep learning systems are super useful. Similarly, these systems are super useful, but be careful about what your expectations are and where the interest comes from. For instance, this example was very pretty, and in fact, much of it is sort of a weird interface, because as he was pressing Y closer to himself, it would sort of pluck again, and at a faster rate as he pressed harder. There'd be timbre changes as he pressed farther away. This sound is still in the continuum. You can, or a very similar one anyway. You can try it. But what is actually going on there? Well, what's going on there is ingenious and pretty, but it's also a very simplified model. So here we go. Waveguide physical models. Now, before they were called waveguide physical models, or I just often call it delay-based modeling, because I like to keep things simple and try to keep a little bit of the magic out. This was invented by Karplus-Strong, and then became this whole, and they made synthesis, they showed the synthesis technique. I don't even know if they thought of it as physical modeling, but then later people did. Said, hey, this is just like, and went from there. And lots of work's been done on it. So what's the idea here? You have a right-going traveling wave. So these are each the little delay things. Each one of these, in the z-1s, right, each one of these dudes here, well, every sample, the one from here goes to there, from here goes to there, from here goes to there. And what is this? Well, it's a delay line, and in this direction, it just tells you, for the right-going wave, what's the string displacement. Here, left-going wave, what's the string displacement? So, if your displacement starts like this, like you're plucking a string, an ideal string, you let go of it, right? You have this triangle shape where, as you're plucking this ideal string with an ideal pluck, and when you let go of it, well, first of all, when you're still holding on to it, you have this displacement of the string, so that's filled into all of these. That's actually just physically displacement. This is physical distance along the string, quantized, of course, but physical distance along the string, and how displaced is it? And then you let it go. So there's a wave that travels to the right, a wave that travels to the left, and they reflect back at the ends. Straightforward idea. Now, I'm describing this right away as a physical model. That's, I don't think, the way it was invented, although my memory isn't good enough to know for sure. I think, in any case, now you add a low-pass filter in the feedback loop. Otherwise, the thing lasts forever. It's kind of boring. So you add a low-pass filter in the feedback loop here. And instead of showing each individual unit, you just z to the minus L over 2 and z to the minus L over 2. Why it says minus L over 2, we'll see in a second. But right, you add a low-pass filter in the feedback loop. So what's going on there? Well, the first time through, whatever spectrum this has, it gets filtered once by your low-pass, or here, whatever the spectrum is for the comes out here for L samples, and then it gets filtered through this low-pass filter, and it gets filtered again the next time through, and the next time through it gets filtered again. So what happens here is, because it's a low-pass filter and it's recirculating, at first you have all the harmonics and everything that's whatever, was in your initial data here. And then that gets filtered down, and it gets more and more mellow. Gets more and more just the fundamental has all the energy. Okay? So instead of doing this thing here, you can take this echo here, you can lump it together like this. And this here is basically what you heard there in that video. But there's yet one more thing to it, which is really important. What is the pitch period here? Well, it's L, right? You can kind of see it recirculates every L. One thing I want to mention here is, instead of actually putting displacement in here, what Karplus-Strong did, and what actually works much nicer for lots of other reasons, just math works out better, mathematical errors, and computation stuff, just put random noise in there, or something like that. Put a bunch of energy in it. It's very bright, right? You know that noise has a flat spectrum. Then it'll look much more like this. Here's your noise spectrum. Then it filters it. It can be gorgeous. And you connect most of the timbre control isn't actually your initial samples here. They just sort of provide initial energy. Well, most of your sound comes from what is this low-pass filter. So on the bottom here, I just want to finish this real quick. One of the problems with this is this low-pass filter here. The period through this is not just L samples, but you have to add in whatever the group delay is through that filter, right? So that's really important, whatever the group delay is for that filter. And this filter probably isn't perfectly linear phase. It's probably different delays at different pitches. So it turns out right away you sort of have in-tuneness problem here. But not only that, whatever this is, you don't want to just control pitch by L, by increments of one sample. So this is just a quickie thing. There is this thing called a Lagrange fractional sample delay. And you can look at this picture. Order 3 is really common. There's the coefficients. Very easy to implement. This just gets you a fractional sample delay. And I want to mention the fractional sample delay because that's how you correct pitch, right? Because, you know, this, here's a different paper, so it's a Z to the minus M that I got this from. But this is the loop delay. This thing here is a really simple filter. Gorgeous, by the way, with this really, really simple low-pass filter. But, you know, how you change A and B here for your low-pass filter and this M, there's some amount of delay here, and then you have to fine-tune it with a fractional sample delay. So I just want to mention this filter because it works way better than an all-pass filter. Like a lot of times engineers will say, oh, I want an all-pass filter. And that'll get me a phase delay. This has better phase properties and stuff than an all-pass filter does. Right, an all-pass filter is maximally flat in the passband, which is cute. Engineers love it. But you know what? In music, how your phase behaves is much more important. So I just want to mention this so that someday if you want to do a fractional, we'll go to filter for it. Thank you very much. Don't get too wet out there. And I'll see you next Thursday, I hope.